So one important case is the log scale. And we basically, this is scientific notation, and this is the way we represent numbers which get very large or very small. So the base we use is 10, and basically we have the form of 10 to the power of some value. And we know that this is really easy to deal with because we basically just shift around the decimal point in order to give us our factor. I'll show you what I mean. So we've got 1.3 times 10 to the negative 3. Let's just say this is maybe this is the current of something. So it's going to be a microamp. This is an amp, and we can represent this as 1.3 milliamps. Sorry. And so we see that you've got 10 to the power of negative 3, which is just the same as 1 over 10 to the 3, which is the same as 1 over 1000. And so you've got 0.001. So this is our factor which we will times the number 1.3 by in order to give us the number 0.0013. Alright. So that makes sense. So let's look at a more chemistry related example, and that's the equilibrium here of water that collides usually with itself, and it forms, it breaks apart and forms protons and OH minuses. Now the protons are so small that they actually will combine with another water molecule, and they'll form H3O+. But for now, to keep the equilibrium simplified, we'll just take the simple form here. So we can write that the equilibrium constant is going to equal the products over the reactants. And we usually write this in terms of concentration, so we're going to have H plus and we're going to have OH minus divided by H2O. Now the concentration of water is basically going to be constant because there's this because we know the concentration of water, and the amount of hydrogen and OH minus that are produced is very, very small, so we usually multiply this through to give us kW. So kW is equal to K times, this is the dissociation constant, times the concentration of water, and that's going to equal H plus OH minus. Alright, so kW for water at room temperature is about 1 times 10 to the negative 7 moles per litre. So you can see here that we're using base 10 system in order to define this. Oh, sorry, negative 14. And so let's say that we're at equilibrium, and that means that we're going to have equal amounts of H plus and OH minus, and so we're going to have H plus is going to equal OH minus, and it's pretty easy to show that two numbers that times by each other to give you 10 to the minus 14 is going to be 10 to the minus 7 moles per litre. Alright, so this is a really, really small number. This is, I'll write it out. 2, 3, 4, 5, 6. Alright, so it's incredibly small. This is a very, very small number, and it would be very hard for us to talk about thousandths of, millionths of concentrations. Because we don't deal with those sort of numbers. We don't deal with millions and billions. So we define what's called the log scale, and the log scale is the negative log to the base 10. So we define the pH as the negative log to the base 10 of the H plus concentration. Okay, so let's work this out. So we've got negative log 10, and at room temperature and assuming equilibrium, we're going to have the concentration of 1 times 10 to the negative 7. Alright, now 1 times 10 to the negative 7, same as 10 to the negative 7, log 10. So we know from the third rule that if you've got log x to the power of n, then you can move the n out the front and you get log of x. So we can do that here. We move the negative 7, the power, out the front, so you get negative 1, because there's a negative 1 in front of there, might as well say it, times negative 7 log 10, and we have the input of 10, and this is defined to be 1. So that makes sense. We have negative 1 times negative 7, and that is 7. And so that's why the pH of neutral water is 7. So that makes a lot of sense. So that's really good. So if we were to let's say we were to add some acid, and the pH was to go to a pH of 1. So we can work that out to be negative log of 10 H plus concentration. So we want to work out what the concentration of hydrogen would be in a pH 1 solution. So we times both sides by negative 1. This becomes a positive. This becomes a negative. And we know that we can rearrange it into the form 10 to the negative 1 is equal to the concentration of H plus. And this is the form of the log. So this here is the base B, this here is our X value, and this here is our Y value. And so we can rearrange that into this form, but we've just undone that rearrangement. And so we can see that this is 0.1 moles per litre. So from a pH 1 change to a pH 7 change is a million times difference in concentration. But in our minds, it's in the pH system, it's only a change of 6 pH units. And so you can see that the 6 denotes how many zeros there are, basically, and it's a small number. So we get